This is the third video for Unit 2. In the last video I talked about heat and temperature. That becomes important when you're dealing with chemicals and living things, because if you lower the temperature, you decrease the chemical activity, and that slows metabolism and slows growth. It reduces the need for food and things that the organism will need to survive. And we can prolong foods by cooling them because it slows microbial growth. We can keep organisms alive in general by cooling them longer. Say if a person were to fall through the ice, they'd have a better chance of surviving without brain damage than if they were to fall in the lake in the middle of the summer for the same amount of time. It just has a great effect on chemical activity. Next thing I want to mention would be the molecule of water. Water is extremely important to life. The chemical formula for it is H2O. Most people would know that. Two hydrogens join to a single oxygen atom. And let me move this over just a little bit. I went onto the internet and I found the web page through a Bing search of the water molecule. The nice thing about this water molecule, it shows how the electrons are being shared. Each hydrogen has an electron, and it shares that electron with the oxygen. The oxygen has two electrons that it will share. Most of its electrons will be shown on the other side. And the oxygen is a much larger atom than each hydrogen atom. So this causes the oxygen to pull the electrons a little bit closer to itself than to the hydrogen. So there's an unequal sharing. This causes the oxygen atom overall to have a slightly negative charge, and the hydrogens to be slightly positive. This gives the characteristic for the molecule to be bipolar, so that the oxygen side's negative, the hydrogen side's slightly positive. That affects how the water molecule interacts with other molecules, and even other water molecules in and of itself. With the one water molecule interacting with another water molecule, you get into the hydrogen bonds we talked about last time. Because what happens is the negative oxygen, slightly negative oxygen of one water molecule will tend to be attracted to the slightly positive hydrogen of a different water molecule. So the different water molecules will stick to each other. If I had the ability, I'd put a positive charge on this side of the molecule, negative charge on this side. And remember the rule, opposite charges attract. So water is described as a polar covalent molecule. It forms covalent bonds, but the electrons are not shared equally, so it causes parts of the molecule to become polar. Kind of like poles of a magnet or a battery. There are three temperatures I want you to be aware of, be familiar with. 0 degrees Celsius, 4 degrees Celsius, and 100 degrees Celsius. The 0 degrees Celsius and 100 degrees Celsius were determined by taking the freezing temperature of water and the boiling temperature of water, putting 100 increments between them, and worked for a very nice scale. Most of the world uses the Celsius or centigrade scale. Americans don't tend to use it except in science, and scientists use the centigrade scale. 4 degrees Celsius is important because that's where water, liquid water, has its greatest density. So as you cool water, the molecules come closer and closer together as you get down to 4 degrees Celsius, and then as you cool it further, the water molecules start to separate from each other. They have more space between them and become less dense, and eventually it freezes and ice is less dense than water, which we'll see as one of the points in just a little bit. Water has a high heat of vaporization. That's one of the characteristics because of the water molecule. It has a high heat of vaporization because the water molecules want to stick to each other, more so than other molecules want to stick. This causes greater heat energy to be involved to try to move those water molecules apart. And so it's possible to have liquid water and steam at 100 degrees Celsius, but there's a big difference in energy value that is in the steam versus that is in the water. It takes quite a bit of energy to cause the water to change state, to separate those water molecules, because you're breaking hydrogen bonds as you add more heat to water that's at 100 degrees Celsius to get it to go to a vapor state. So it takes a lot of energy to get it to go to a vapor state. This becomes important also in cooling, not just in boiling, but just water evaporating. It pulls heat energy from a surface. Water also has a high specific heat, and what that means is it doesn't gain temperature or lose temperature very easily. It helps to moderate the temperature of living organisms. And this is a great thing because living organisms have a lot of water. It's said that our body mass is about 3/4 water. So one of the ways that you can tell the health of a person is to take their temperature, and that's fairly constant. Unless a person's been exercising or they've been at rest for a while, it'll change a little bit. More so if they've been exercising. Because the water helps to moderate the temperature. So you'll see great temperature swings in the air, but not so much in water. It takes a while for water to heat up or for it to cool down. The other terms I have here that characterize water is it's cohesive, it sticks to itself, and it's adhesive, it sticks to other things. This is by the hydrogen bonds. Water will stick to glass and plastic, to skin, to paper. This is an especially bad time to do it, but it's not healthy to do it other times. But when most people lick their fingers and thumbs to turn the pages of a book, they're actually putting down microbes when they do that. And especially in the cold season, flu season, it's a good way to spread those viruses. Capillary action, this is what you see with water climbing substances. You can take a paper towel, put it on the surface of water where the paper towel is vertical, and the water will climb up the paper towel. It'll do this inside plant tissue. This has been used to describe how water moves up plants. They don't think that entirely describes it, especially tall plants such as the trees that are well over 100 feet tall, in some cases over 300 feet tall. They think there may be something else that's going on. Also, you see surface tension of water. The surface tension is so strong that you can float a needle or a paper clip on the water. If you put the metal carefully on the surface, it's not because the metal is less dense than the water, it's just because of the surface tension. If you were to pound the surface of the table on which the container is sitting that has water, it will shake the water molecules, and your needle or your paperclip will sink. If you ever want to try this, you can also magnetize your paperclip and your needle and use it as a magnet. Another characteristic of water is that it's less dense than liquid. The characteristic of ice is less dense than liquid water, and therefore it floats. We take that for granted, but that's very important in the winter months, especially over the last month that we've seen with extremely cold temperatures, where the top surface of the water will freeze, but it doesn't freeze all the way to the bottom of the pond. That's because the ice actually acts as insulation. As you go farther north, up into Ontario, you may find that the ice depths reach 3 or 4 feet, depending on how long it's been cold. I was in Canada a few winters ago and watched a guy drill through the ice, and it was between 3 and 4 feet in March. They had a relatively cold winter that winter, not the coldest that they'd seen, but ice can become very thick where they actually drive heavy equipment across it. Water is a great solvent. Some describe it as a universal solvent. It doesn't dissolve everything, but it dissolves many things. In ending up the chapter, or actually this unit, I need to discuss pH. The pH scale is a logarithmic scale. It's used to describe acids and bases. Generally, you think of acids as being below a pH of 7, the bases being above a pH of 7. And because it's a logarithmic scale, the difference between any whole numbers, successive whole numbers, would be a 10-fold difference. So if you have a pH of 7 versus a pH 8, there's a difference, a 10 times difference in the amount of base that's present. If it's a difference of 2 whole numbers, say 6 to 8, it's That's 100 times difference. So an 8 is 100 times more alkaline than a pH of 6. That pretty much brings us to the end of the second unit. If you have any questions, be sure and contact me.